Okay, we're recording now. So let me know if you can see my screen and my slides. Yes? People can see this?
Yes, sir.
Okay, cool. All right, any questions from yesterday? If there are, I can quickly take it or we can move forward. Okay, so yesterday we saw an introduction to convolutional networks, right? And we kind of talked about what they do, what is the history, where was the inspiration from, and what particular applications that it can be possibly used for. So we discussed a little bit about that. Today we'll go into some of the technical details, right? So split the convolutional neural networks into three things, right? Like we have the convolution part, right? The pooling part. And then finally, this part depends upon the type of application you want the neural network to do, right? And most of the times these are fully connected layers because we are interested in doing image classification. But as I spoke yesterday, this can be replaced with anything, because what you get at the end of as you go deeper into the convolutional neural network are more abstract representations of the image. So that can be used for pretty much anything, right? So that's the idea. So let's look at first thing starting off with is the convolution operation. Okay. And I use the word kernels because there is a reasoning behind why you would call it a kernel. All right. So it is very important to understand the idea behind convolution, get a good grasp of the not just the math, but the intuition behind what convolution actually does, right? And understand that the convolution can be done in any dimensions. Although convolution was initially a time domain operation, right? So if you have a time series signal, right, something like that, and then you can convolve a time series signal with another time series signal. That was the idea, right? So some signal like that. And the mathematical operation, if this function is say f of x, or I would say f of t to be more precise, and this is g of t, right? Mathematically was represented by this star operation f convolved with g, right? And you integrate from minus infinity to infinity, right? You take the function and you take a small piece of the function, say tau, so small time segment, and then you take your another function and then you flip it. That is, if the function is like this, you mirror the entire function. That is, you take this and you put this at this end. So if I just take the mirror of this function, something like that, right? It will look like that. So that's t minus tau. So some part of that. So you just flip it and then you integrate it across time. All that means is that you take this function and you slide it over this function, and then that's the convolution operation. Okay, mathematically that's what it is. Okay, but can anyone tell me what does that give us? Any idea? What is the motivation to take a function like this and slide it over another function and get some output? What sort of um, motivation is there to do this form of an operation?
Projection of one function
One
to
function onto another, and the projection would give you what information? Like what is,
Intersections.
sorry?
Intersections.
uh be more
Multiplication.
precise. I see what you are trying to say, but try to be more precise.
so it will give the hidden concepts in that function, maybe summarization or maybe integral of it kind of
Yeah, but the integral in fact is like you are taking a section of this function and writing over it, and you are taking the overlapping areas, you're taking a sum of them. Actually, you're multiplying both of the functions and taking a sum. In fact, it's a dot product, which we'll discuss little bit later. But people are somewhere close. They're saying,
area
okay,
area under that.
yeah, area under that. But what does area and area interpreted to
Approximating,
be?
basically approximating with the help of multiplication.
Mm, yeah, people are all around the area. You're sort of not hitting the bullseye. You're sort of a little bit around it. But uh, what it actually gives you is a way to do pattern matching. Okay, see, this is very important. Okay, that means that if there is any part of this function which has something which is similar to this function, right, the area under the curve will be bigger. So that means that there is, when you project, and when someone said project, right, that's correct. When you project this function onto this and slide it across, you can find those areas that actually are similar to this particular function, right? Like if there are places inside this function which have certain oscillations that match this
Kind of
frequency, then you can
in,
sorry.
interference.
Uh, yeah, you can say that, but it's more like there are places where it will constructively interfere to give you some form of feature matching, okay, or what's called pattern matching. Okay, this will become a little more concrete as I go forward, but I want you to understand that when you do this mathematical operation, what you are actually doing is a way to understand if there are some features of this function that match this function at some time point. Okay, and the sort of leap from here is that this is a 1D signal, right? Like this is a one-dimensional signal. If you can think of, if there's some finite time capital T that this function goes till, or even till infinity, does not matter. It's a 1D function. And in fact, what people saw was you could do this spatially over a 2D, or in fact in n-dimensional entities, or data can be subject to convolution. And it becomes very interesting when you go to 2D and 3D what the output of convolution actually gives you. Okay, but if you understand that the consequence of convolution helps you do pattern matching and a way of doing feature extraction, that's the main thing I want you to take away from this. But we'll exactly see how that is done in the next coming slides. Okay, all right. So in order to understand convolution, let's take the 1D example, right? Let's do that. Before even going there, we should talk about vector dot product, right? So come back to a little bit of linear algebra. So what's a vector dot product? If I have two vectors like this, and I have to take the dot product between them, how would I do this?
X is y.
Product of sum of consecutive elements.
And the integers, yes, elements in the thing. So something like this. So if this is v1, this is v2, so v1 transpose v2, right? If you do that, you basically get some answer, right? This is basically the dot product. But what does the dot product actually give you? What does it tell you about the two vectors?
What is the projection of one vector over the another?
Okay, but projection is one thing, but what does it actually mean?
X is
तो वो
y.
पॉइंट पे मतलब एडिशन टाइप की फीलिंग दे रहा है, जैसे सेम शेप है तो ऐड होके बढ़ जा रहा है एम्पलीट्यूड.
Say, फिर से बताओ, what are you trying to say?
Like amplitude will got added at that
Okay.
point.
So what does that tell you about these two vectors?
Like if same shape of the curve is there, then it will be
No, it's not
maximized.
same shape, right? These are vectors, right? Like if this is a 3D point in space, like that's the vector. There'll be 1, 4, 5, and there'll be another 2, 4, 6.
Resultant.
No.
So it depends on the type of vector. It will give the physical significance if you define a type of.
No, not necessarily. Mathematically, I can define a quantity which will be a consequence of a vector product. So, okay, let me ask you another way. If this vector dot product is high or low, what does that tell me about these two?
So if they are high, basically they are in the same direction.
It tells about the
That's it.
overlapping of two vectors.
Exactly. Absolutely. Very nice. So in some sense, it tells you about the similarity between those two vectors, right? In space, it can also tell you about the angle that's subtended between them, right? So in a way that tells you about some form of similarity pattern matching. Okay, so this is the takeaway, right? The bigger the dot product, the bigger the similarity between these two vectors in some sense. Okay, now we'll talk about the idea of a signal and kernel. Was there a question? You can just shout it out. Okay, unmute yourself.
So like अगर हम if we see this numerical dot product, so like जैसे एक वेक्टर आपने लिया है 1.5 and second you take 230 500. So if you do the dot product, then numerical will very high, right? But
fine, yeah, you can normalize them. That's okay. I mean, there are things to be normalized here. I'm just giving you a very simple example, right? Still, things can be normalized and made unit vectors where we just know their direction. We don't care about their magnitude. Right? There are ways in which we can do that. So that could still be something that scales up, but in terms of similarity, then you can normalize them too. I'm just giving you a very simple basic idea. It's yeah, if you want to actually find out the projection, you have to divide it by the norm of the vectors, which is a way to make them unit vectors and then do the comparison. But this idea is important to know because we'll talk about how convolution works, because convolution is nothing but a vector dot product. Okay. And how does that work? Let's take the idea of a kernel and a signal. Okay, I'm going to just erase this. Okay, the idea of a kernel is some form of a function that you are trying to look for in the signal, or you are trying to use this kernel to do something on your time series signal. Typically your kernels are smaller than your signal. Let's say this is a type of signal that you have. Okay, and a convolution operation typically is represented by this star. Looks like this. Okay, now I'll show you the output of convolution. Your thing would be to tell me what is the interpretation of that, right? So this is how the convolution result looks like. Okay, for when I convolve this kernel onto this signal. Okay, that way what I'm trying to do is take this kernel, place it here, take this particular section, take the vector dot product of both these, and then wherever the center of the kernel is, that's where I'm putting a point. The result of this. Then I'm taking this, I'm sliding this over. Okay, I'm taking the next window, computing the vector dot product, putting the result, and so on and so forth. So as I shift this kernel over the signal, and this is the output that I'm getting. Okay, so anybody can tell me why this output looks like this, or what's the features of the output that you can tell me that seems to be the output of these the convolution of these two things?
The peaks and the
Smooth version of the signal.
Very good, very good. So the signal is smoother. Okay, in some sense the signal seems like a mixture of both the kernel and the original signal, right? In some way, that these peaks that were much more prominent have now gone. Okay, what else? Was there a question? Just, yeah, you can just unmute yourself and ask. The other thing is, you can imagine if there are any places in the signal that look like the kernel, right? The vector dot product will be high, and that will lead to a higher signal value, right? For example, these places kind of look like your kernel, right? And so the value of the dot product will be higher compared to those places where it does not look like the kernel, right? Now, this will be much more apparent if there are more features in the signal that look, where you pick a kernel that looks like part of the signal. That's a different thing. But in this case, you can see that the output of the convolution is a mixture of both the signal and the kernel. And you can see that there are certain places where the convolution gives you a high result and then it gives you a low result, right? And the way convolution is actually done is very simple. It's just taking this kernel putting it onto the signal, okay, and taking the dot product of that particular section. So, and then moving it further along the signal, and you get this result. Okay. Now, can you see how convolution can actually do pattern matching? Because if there was any part of the signal that matches, say, the shape of the kernel, then because those two vectors are similar, their dot products will be higher. And those places where the result of the convolution is high tells you that there was more similarity between the kernel that was used and the part of the signal that it was looking at. Is this idea clear? Yes, because understanding this, if you get this idea, then looking at this in 2D and 3D all will make sense.
So could you please repeat once? Thanks.
Right. So the idea of pattern matching is that, so you know that for a vector dot product, if two vectors are similar to each other or if they're same, then it will give you a the dot product will be higher compared to
Yes. Yes.
So if there is any part of the signal that looks like the kernel, when you slide the kernel, and let's say this was the part of the signal that looks like the kernel, let's say, if you pass the kernel on top of this area as you are sliding through, the result of the convolution will be higher at that point, right? Compared to the other. So what that tells you is that it is used as, and the reason then it's called a kernel is like, now you're looking through this signal and identifying those places in the signal where it looks like what the kernel is, right? And because at that particular time area, you will, or at that particular time point, you will get a high value of convolution. Okay, so you are able to extract from the signal those locations where it matches your kernel. Okay. Now, if I want to find out different properties of the signal, not the places where it looks like this, what would I have to do then? So if I want to look at those parts of the signal where the signal looks like this,
we can send maybe a step function or something as a kernel.
As a kernel. Very good, very good. So you change this kernel. So if you get this idea, you will get a lot more understanding of what convolution is. So you change this kernel. All right. So if by changing this kernel, as someone said, to a step function, for instance, or a box function, for example, now those places where you see these, increases, I mean, this is a box function, basically, a summation of several box functions, but I'm just giving you an example. Okay? You are interested in these small peaks. So wherever this particular kernel overlaps with this signal, those places, the result of the convolution will be high. So in essence, these are extracting out features from this signal based upon the type of kernel that we use. Okay, and the way that's doing it is the kernel is being slid over the signal, and you are computing the vector dot product at every time point. And by the properties of vector algebra, those places where there is similarity between the kernel and the signal will get a high value. And that's basically the output of convolution. Everyone on board with this? On the same page? Yes? So that's
Yes,
the idea behind this.
Sir, I have a question.
Yeah, please.
So last day, when we are actually looking at that particular frisbee picture, so you said that means a small section of a collection of pixel from that particular picture is kernel. So right now we are.
No, I didn't say that was a kernel yet. I never talked about kernels there when I talked about pictures. I was only talking about spatial correlation. That is, when you look at a small part of the figure, there is spatial correlation, but kernels are very different. I'll come to this in a bit, okay, how it works in 2D and 3D.
Okay, sir.
Okay, cool.
Sir, is there any particular reason why this kernel is a Gaussian type?
Sorry, why this kernel is a?
Is of Gaussian.
Oh, is a Gaussian? No, not necessary. This is just an example, right? As I told you, depending upon what sort of thing you need, you can change the kernel. But in fact, I'll tell you what CNNs actually do. You don't have to even find this kernel out. What you are training the CNN is to actually find out such kernels or optimize such kernels. That will extract whatever features that you want, which will maximize certain objective function at the end, right? That is to classify an image. So we'll talk about that. But what I'm trying to say is that this is just an example to illustrate the idea of convolution. This could be anything. Okay.
Yes.
All right. So another small, how would I say it? Slight subtle point, which typically, people ignore, but I just want to put it here. As I told you, convolution is an operation where you actually flip the kernel. Okay. But if the kernel is symmetric along its center, like for example Gaussian, it does not matter, because if you flip it or if you don't flip it, it does not make any difference, right? But if it is a function like a sawtooth, like that, right? If this was your kernel, for example, I'll always call my kernel G and my signal F. Okay. So if this was my kernel G, right? Now, when I do convolution, you typically will flip. Okay. That means you'll flip this signal. So this is G of t minus tau, right? You flip this. Okay. So then you slide it over. That's convolution. But if you do not flip it and you just do, you slide it over and compute the result, this is often what's called cross correlation. Okay. This is convolution. So there is a slight mathematical difference between if you flip the kernel, if you don't flip the kernel. But if your kernel is symmetric, then cross correlation is the same as convolution, right? At that point, it does not matter which orientation the kernel is in. Okay? So that's slightly a mathematical point just to know, because it does not matter in case of CNNs, because the kernels are actually trained instead of us hand designing them. But just a point to note. Okay. All right, guys. So moving on. So let's take this to be a signal and this to be the kernel, for example. Okay, this kernel is like a simple straight line. And as I told you, what you're doing is that you are pasting the kernel onto the signal, taking the dot product, multiplying them, summing them, and then that's your result. Okay. And if you do that across the entire time period, this is your result of convolution. Now, can anybody give me an observation of what the result is? Anything about the result that's peculiar for this particular signal and curve?
The points are continuous as compared to the original signal.
That's fine. I mean, you mean to say here you see that there is more, the points are, or the function becomes a little bit more smoother and continuous. That's okay. But can you tell me about something about the size of the result?
DC value is a bit moved up.
But can you comment on the size of the result?
The result
Zero
is
size.
Sorry? Come
the
again?
result is much wider than the signal.
Wider or?
I think it's almost the same.
Means on peak it's small, but at the bottom.
So the number of points in the results is the same as that of the signal?
There are more points.
Yeah, more or less?
Slightly more. More.
Reducing.
Less points.
Yeah, tell me
Just
correctly.
significantly
number of points.
There are less points in the
Yeah,
result
reduction is there.
than the
So
signal.
dimensionality reduction is happening.
Exactly. There is less points in the result than in the signal. The reason being that when you slide this kernel off, you are plotting the result of the convolution at the midpoint of the kernel, right here. And then you are sliding it one step and then doing the same thing, right? So these points here at the end, we do not place the kernel on so that it's centered on those 2 points, right? The first point on which in the signal where the kernel is centered is the third point, and the last point at which the signal is this kernel is centered onto the signal is this second last point here. So in essence, in the result, the result is 4 points less than that of the signal, right? In this case. So tell me now, if I have to get the result the same size as that of the signal, what would you want? How can you do that?
We can add some buffers on the side.
Very nice. Yeah. And in fact, this is what we often call as zero padding. That is, we pad the signal with some zeros on either side and start the convolution such that it starts at the, or you can slide it over and you will get the same result, or you can chop off the signal in such a way that it will be at the same length as that of the original signal. Okay, so these are some subtle tricks that you do. Even in CNNs, you will see that we'll be doing some idea like this. Okay, so zero padding is another important idea in convolution, so that we do not because of the operation of convolution, we do not lose any data from the signal. We can zero pad the signal in order to get the result to be the same size as that of the original signal. Okay, the result of convolution. All right. Okay, cool. So that's
So one more thing.
Yeah.
So here, what is the difference between the B and C?
So
Or second
B
one and the
and
third.
B and C, right? So here you can see that the result is shorter than that of the signal, right?
Correct.
Because you see that this is the case. But here the signal size and the result size are the same. The reason being that you zero pad some of these the edges of the signal, so that now you can start the kernel even before, so that as it slides through, you even take into consideration the earlier the first part of the signal and the end parts, right? So you don't miss on them. So this way you can make sure that you don't lose information as a result of convolution. And zero padding is one of the ways in which you can do this.
Okay.
Okay.
Okay. Thanks.
Okay, guys. Sound good? Now, let's look at how this works in 2D, because we are dealing with images, right? We're dealing with image data, and it's often important to understand what is happening in such a case where you are operating convolution in 2D. Okay, so let's take a very simple example. Before we actually go into 2D data, do you know how to do dot products in 2D? So let's say I have a matrix instead of vectors.
One row, one column multiplication.
Yeah, every same thing, element wise. You do 1 times 2, minus 1 times 0, 3 times 1, and then so on, so on, so on, and then you sum it up, right? And that's the result of a 2D dot product. Okay, so that means that this time you have an image, and you can imagine that there is a kernel which is probably smaller than that of the image, and what you are trying to do is you're going to take the kernel and you're going to slide it over the image. Okay, so let's take a very simple example. This is my image. Okay, so if you can see, this image is just pixel intensities of zeros and ones. So if I look at this image, this will be an image of an H, right? So there is an H here. Okay, so Yeah? So these are all ones. This is all zeros. Okay. So that's what that is. And then what you have is a kernel. Okay. The kernel is typically smaller than that of the signal, because what at the end of the day we want as a result of the convolution is to look at small parts of the image and extract features from those small areas of the image that has some similarities with the kernel. Now, if you can imagine what this kernel is nothing but a small piece where this is all ones, this is all zeros, this is all minus ones, okay? Something like that. Okay, that's your kernel, and you're convolving these two things. So how does 2D convolution work is I take this kernel and I place it on the image like this. Okay, so I'm mapping the kernel onto the image, and I take the dot product. All right, so that means that I'm going to place this kernel. I'm going to do 1 times 1, 0 times 1, 0 times 1, minus 1 times 1, and so on, so on, and so forth. Right? And then I'm going to take the sum of all of them and put that as an output. Okay. Then what I'm going to do is I'm just going to slide it 1 time over. And then I'm going to do the same thing. Then I'm going to slide it. Okay. And I'm going to go down this time. So once I reach the end of the image or end of the 2D thing, I bring it down 1 row and start again. Okay, from the left point. And then I slide it such a way, and then this is the output of my convolution. Okay, in 2D. So in terms of the mechanics, this is how it operates. All right. And if you can see that when I go over this image like this, what can you tell me about the output of the convolution?
Signal loss again.
Sorry?
Again, the original signal was lost.
Yeah. Or the output of the convolution is smaller than that of the signal, right? So output is smaller than the image, right? And one of the other things that you need to note is the kernel that we have taken, the original size of the image here is 5 cross 5, correct? The kernel is 3 cross 3, and the output of the convolution is 3 cross 3. And one of the things that you need to realize about the kernel is that the kernel, if it is an odd kernel, right, it is easier to do convolution, because if it is 3 cross 3 or 5 cross 5, why do you think so? Any idea? If it's odd, why is it easier to do this operation?
That it has a clear middle point.
Yeah, absolutely. It has a clear center, right? So when it has a clear center, then it's easier to actually do the operation and know where to place our result, right? So typically you want to pick, sorry?
By it's have a clear center, so what is the advantage of clear
What is the advantage when you place this on top of this? Let's take this, right? The output of the convolution can go bang on to the center pixel of this particular cell.
Okay.
But if it was a 2 cross 2, then you don't know where to place the result, right?
Mm-hmm.
So that is why it is often advantageous to have a kernel which is odd numbered, right? odd numbered kernel. Okay, got this idea, right? So that's the idea behind 2D convolution. It's very simple. Yes. Now, if you can imagine, what would you want to do if you want the output of the convolution the same size as that of the image?
Padding.
Padding, yeah, very nice. So if you zero pad it all the way around, which we will also discuss, then you will be able to make sure that this is the same size, right? Yeah, any questions here? It should be very straightforward, right? Okay.
After padding, what should be the size of the image?
Sorry?
After padding with zeros, what should be the original size of the image? It should be 8 by 8 or how?
No, okay. We'll talk about padding a little bit. So if you just be patient for 10-15 more minutes, we'll talk about padding. We'll say separate them.
Yeah, one
But
more
we'll do it. Yeah.
When you talk about the kernel size, the output will always be equivalent to kernel size if we don't have any padding, or is there like if it's a
no exactly, that depends, right? If the kernel is 5x5, right, and the images, so there is a way in which there is a relationship between the number of pixels in the image and number of size of the kernel, which we'll discuss. In fact, there's a simple way to estimate what is the output of the convolution based upon these two things. It won't be always the size of the kernel. Okay, so it's not, in this case it happens so, right, given this thing, but there is, you need to understand two more ideas before I go into that. There's an idea of stride and padding. Those two things, if we discuss, then we'll go into that. Okay, before, so otherwise it will just the flow will not be there, right? Slightly jumpy.
What about inversing the kernel like we discussed in the previous slide,
like deconvolution, you mean, right?
Yeah.
So that's pretty simple, right? You just do the inverse operation right now, right? Like instead of taking this through the kernel and then taking the sum, you're sort of now asking the question how to take this one pixel and deconvolve this, right? Now for that also you would need a set of kernel, right? Like you need to know what and that's a slightly different topic of which will
no sir, I was not referring to that.
Yeah.
In the previous slide you said when you given a kernel you should take the like you took the example of that saw kernel, right? You told it to inverse it so that
okay, very good. Oh, I see, inversing that. Yeah, so that's what I'm trying to say. It does not matter too much if you inverse it or not, because at the end of the day what is happening is that I'll tell you that this is not something that we set by hand. This is what is trained, right? This is what the kernels are basically trained. You get the values of the kernels by backpropagation. And at the end of the day, it does not matter if it is the straight way or the flipped way. So, okay, so if you are flipping it, then the network will adjust its weights in such a way that when you flip it, it looks like this, right? If this is what the kernel at the end of the day, it's optimal, right? So it does not even matter too much. That was just a small subtle point, because you will see in some places cross correlation being used. So you should know that cross correlation is very similar to convolution. It's just that the signal is not flipped when you're doing cross correlation. But for the intents and purposes of a CNN, you do not have to worry about whether the kernel is flipped or not, right? So if you even flip the kernel, whatever output you're getting, you're flipping it and then you're doing the convolution. If that is the way you're doing it, then what the network will learn is that it will learn in such a way that when you flip it, it will look like this. Okay.
Sir, it has to be square, or this is just an example?
It's just an example. Typically, it is square. The reason being, as I told you before, right, when it is a square and an odd numbered thing, it's easier to do the convolution and place the result, right? But it doesn't necessarily have to be. Okay, it can also be a rectangular kernel and so on. But there needs to be a motivation for why you are using that, which we'll actually look at how kernels are used and what sort of output they give you. That will make everything a little bit more clearer. So typically they are square. Okay, but necessarily it doesn't have to be. You don't have to impose that constraint. Okay.
Yes.
All right. So let's take this example. Okay, this is an image of a B. Okay, this is that same kernel that we have been looking at, right? This one where it's 1 1 1 at top, -1 -1 -1 0 0 0. Okay, and this is basically the image. So this is an image of, say, the letter B, for example. Now the output of the convolution looks like this, right? Yeah, this is again the sides are not there, no values there. It looks like this. Now if I rotate this kernel and then rotate it like this, yes, and then place it and now convolve with the image, the output looks like this. Okay, now what can you tell me about the output of the convolution here and here? Sorry, what does it actually tell you about the image?
One is detecting horizontal edges,
Very
one
nice.
is
Very
vertical
nice.
edges.
Very nice. Very nice. Cool. So now can you see how the output of convolution gives you something about the features of the image, right? So in this case, when the kernel was in this orientation, it was sensitive in picking up some of these horizontal lines in the image, right? At least it's picking up these two, or because the image is of very low resolution, but still puts the point across. And the same thing, when the kernel was rotated, now it's sensitive in picking up these vertical lines, and that's what it's doing. So can you see that the output of convolution goes from images to certain features of the image that we are interested to extract. All right. Now let's extend this to 3D now. Okay. Now, okay, I just revealed it. What could be 3D data? I just showed it to you guys, but you can tell me. So when would you encounter three-dimensional data, especially in images?
Or videos.
Videos is fine, but for say a static image,
With the depth.
RGB images.
Yeah. RGB, right? RGB, red, green, blue filters are each one dimension, right, of the image. So typically for a image, you have the size of the image. Let's say the size is 250 cross 250, and then times 3, right? You have sometimes 3 dimensions for R, G, and B if this is a color image, right? So that'll look something like this. Okay, so now you have convolution in 3D. Okay, so what can anyone tell me what the kernel will look like for such a, what would be the dimensionality of the kernel?
It will also be three-dimensional.
Three-dimensional, right? So it has to be this way, correct? So let's say something like that. And how would the now 3D convolution work?
Each layer will convolve with each layer and will give a 3D output.
You're doing convolution, so you'll have to add up everything then also. That's correct. So you place it here, you place the kernel here, right? And then you sum up every entity with each, and then you sum it up, and then you get your convolved output. So this is one kernel, right? This one kernel having 3 dimensions. Okay, right? And that's your convolved output. Now let's say, for example, I have 2 such kernels. Then what will happen is you'll have one result because of convolving this kernel with the input image. So that will be this, right? Yeah. And then there'll be another kernel which will convolve with this image, and that will give me another. So the output convolved, the convolved output now can be basically the number of kernels that you have applied to this signal. So if you have a M-layered kernel, right, you'll have an M-layered output. Now, what sort of kernels can this be? Let's say this is RGNB. So to think about this, so if I take this specific kernel, what type of kernel could this be? This could be a kernel where this is a sort of a red filter, right? If it's a red filter, then what sort of a kernel could be? It will be all ones here, right? And it'll be all zeros, right? So this sort of a kernel will implement a red filter. Right? And maybe this is a blue filter, for instance, right? So what my point is that the kernels can be now used to create specific types of features. Now this will be a feature map where the image is red filtered. Right? So now the point is, can we then identify specific kernels that can give rise to feature maps that will solve a specific objective, which is what CNNs are all about. Okay, this is okay? All right.
So one question, sir. Like, for example, if there's a 3D input like image and we give a one layer of only one kernel, one 3D kernel, so the convoluted output is a 3D convoluted output, or it's a 2D?
No, it's a 2D. Okay, so you'll only get this.
Yes.
Yeah. So with 3D convolution, you will, with a 3D kernel, you will only get a 2D output. Because when you convolve it like this, you are not doing individual layers. You are adding all the layers across as well. Okay. So you are multiplying individual elements and then adding it across this and across this. Right. So that's what you do in 2D, right? So if you imagine here in the 2D case, you are placing the 2D on this and getting a 1D result, right? Yes. At the end of the day. So the same thing happens here in 3D. Right? When you place it on here, you get a 2D result.
Okay.
The output is always 2D. Yes. That's why you need, when you add one more kernel, then you add one more layer to the output. And the output, convolved outputs are often what are called the feature maps. Right? Feature maps. Okay. All right. So just to reiterate some of the important points here. The important points here are we can take care of the edge effects using padding, right? We will discuss a padding a little bit. We'll talk about stride and pooling a little bit later. But the idea is M kernels lead to an M layered result, right? Because if you have M kernels, as you see, you will get an M layered result that is irrespective of whether it's 2D or 3D, right? Like even in 2D case, if you have two kernels at that same layer, you will get a 2-layered output. So one layer for convolution with one kernel, the other layer for the convolution with the other kernel. Okay. So at a given layer, you can have many kernels if you want many such feature maps at that level. Okay. And as we saw, it's beneficial to use an odd size kernel. Okay. Now, I just gave you a small brief intro into this, but let's talk about padding and stride. Yes, because this is something that we are talking about, and let's just finish that part off. So what's the idea of padding in case of 2D convolution? 2D convolution is more common. We are probably very likely to use this So this is what the situation was, right? We have the image, we have the kernel, we have the output of convolution, which is smaller in size compared to the image. And what did we say? We can pad this image. So one of the ways in padding this image is often what's called zero padding. Okay. So now what you have is zeros all around. So the image now, instead of becoming 5 cross 5, it's now 7 cross 7, right? Seven this way. Yes. And now the output of convolution becomes much more easy because you can now place the kernel here. And this way you get an output even at one of the edges of the images. Right?
Sir, how is this useful? Like in a sense that since convolution always tries to lowers the dimensionality.
We typically don't want the output of convolution to be lower dimensional most of the times. It can be fine, but we use stride and pooling, which are those two methods, to actually reduce the dimensionality. Okay, so we don't want to decrease it at this level. We want to use after this, either at this level we use stride, which I'll talk about, or we'll follow this by pooling, which is where we want the dimensionality reduction to happen. Okay, not at this level.
Sir, so in that sense, this is actually just to define the features in that sense.
Exactly, right? So you're sort of covering the entire image and not just leaving out the edges, which might have some significance in some aspect, right? So we don't want to get rid of those. We still want some information from the edges of the images. So that's the reason why we do zero padding. Now, can anyone tell me, is there another way to do padding that is different from zero padding? Is it possible? Any ideas? Can you do padding in another way?
So we can just copy the one that, like, all ones are there in the.
Very nice. Very nice. Very nice. Yeah. So what we could do is, if this is the image, right, the center one, we can flip this image in such a way that the bottom comes back on top here. That is, we roll the image like a torus. That is, we roll it this way, and then we roll it this way. Okay. So this is often what is called circular convolution. So you are doing convolution on circular data. That is, now zeros will come back here. So in fact, you can imagine as if taking this part of the image and then putting it here. Taking this part of the image, putting it here. Taking this top part and putting it here. Taking the bottom part and putting it above, right? In some sense, this is also a valid way of doing padding. Now, what you are using is the data itself to circularly move it around. Yes. And this is also another form of convolution that you want to use. Because sometimes what might happen is, if you zero pad and use zero padding, and that might produce more distortions at the edges of the images compared to the center, right? So if you want this image to still be smooth, because then what might happen is that the spatial correlation would still be maintained even if you go towards the edges of the image, right? Like if you can imagine at the edges of the image, if there is nothing around it, then you lose this spatial correlation property, right? So by rotating this or by flipping this image up, down, right, and left, you can create a circular convolution, and that way you will have much more smoother convolution at the edges of the image, or smoother results.
So top of the image will get correlated to the bottom of the image.
Yeah, yeah. So you will basically flip this around. Yeah. That is this way. You go this way. That is, if you take this image and then invert it like this, that is, the top will be just replicated this way. Like if the if there's a signal like this, something like that, you mirror this. Like that. Yeah, so there's a mirroring. So here, if you place this in front of a mirror here, let's say, then you will see that these guys will be up top, right? And so on and so forth. If you place a mirror here, then these guys will be next to it. Ones will be next to it. Zeros will be far away. And so on and so forth. So it's like a way to circularly convolve.
Sir, but at the corners, the elements will be left vacant. Will we replace them by 0?
Oh, yeah, yeah. Here, at these corners, right? We can do that. Or we can even, do this. Take this corner and then put it here.
So, sir, one thing I am not able to understand. Like, flip के बाद वो data कैसे बनेंगे? Prepare कैसे? Table कैसे दिखेगा?
It's be like the same image, right? I should have maybe had an image like that. Okay, so maybe I'll erase everything and then I'll show it to you. So if this I have to do circular convolution, it will look like 1 0 0 1 0 here. Okay, this is 0 again, so this doesn't matter. This is 1, so this will be 1 at this edge. Okay, because this edge is 1, it'll come back to this edge as 1. Okay, and then so on and so forth. So this side will be 1 1 1 1 and 1. Okay, and then so on. So you kind of flip this 0 0 1 0 0, right? And then 1 1 1 1, and then 0 0 0. So you just flip it, and this way also the same way, 0 0 0, and then comes. So this way what happens is that there is still continuity in the image, right? In all directions.
So these are same thing, or circularing or mirroring are different?
Sorry?
One thing is circle, one thing is mirroring. Circle where you told me that the bottom will move.
Bottom will come on top. That's circular convolution. This is a mirrored version of that. So there are two ways in which you can do this.
Yeah. So one is circular,
one is circular, and one is mirroring.
Okay. So in mirror also, sorry, circular, the left will go to right, right will move to left, right?
Left, yeah.
Okay.
So in circular convolution, you can you think of as you are folding this way, and you're folding this way. In mirroring, you see as if you are placing a mirror here and a mirror here, and that way things will flip in all directions, right? So there are multiple ways to do padding. Zero padding is the best. These are certain variations of that. Okay, and there are certain reasons why you would use it. I'm just giving you some details here, because in certain images you still want the edges. If the edges are important for you to actually tell you something about the image, right? That might be important, and so you want to preserve those and not have any artifacts there of these edge effects. Then you would use something like this. Okay. All right. Now, there's another concept called stride in 2D convolution, which helps us actually reduce the result of the convolution. So let's take this example, right? Like where we are placing this kernel onto this zero padded image. Now, instead of shifting the kernel every time by a single unit, you can do this by shifting the kernel onto the every second element. Okay, so first the kernel is placed here. Okay, and next time, instead of being placed in this, it's placed here. And next time, instead of this section, it's placed here. Okay. Now this is what is called convolution with a stride of 2. Okay. That is, instead of moving 1 step, you are moving 2 steps. Okay. So the output of the convolution won't be this. It will look like this, right? So the output would be every other element here. So you will see here first this one, then this one, then this one. Then here there will be nothing. This won't happen because this way also you are moving 2 steps instead of just 1 step. So then the kernel will be centered around this. So you'll get this result, and this result. And then this, and this. Right? So this way what you are actually doing with stride is you are doing convolution, but also finding a way to reduce the dimensionality of the output of convolution. Or
so any advantage to reduction in
yeah, so this might be done in case of images that are highly in, you know, there are very many pixels in the image, right? It's a very high resolution image, for example, right? And downsampling helps a lot in those cases, right? Like you want to downsample the image, and what you can do here is that you can extract the features of the image using the kernel and downsample it at the same time, right? You don't need all that information to be preserved, right? So that way it helps us improve the performance of the model. So these are all parameters that you can play around with, right? And it's often very hard to decide what to actually do. It just based on practice and you working with these models for a while that you understand that, okay, if I have an image of really big size, then I don't need to have all the dimensions or all the pixel values in the next stage of my features. So what I can do is I can apply a stride of 1, 2, or 3 and reduce the or downsample the image, reduce the dimensionality or downsample the image. Okay.
Sir, is it based on the idea that, like you earlier taught, that the near pixel will always have similar information, especially in the high resolution
Very
pictures?
good, very good, very good. Yeah, that's basically it, right? Like imagine that image that we had where the man is walking the dog. If it's a very high resolution image, in the near my pixels will pretty much contain the same information, right? We don't typically need all that. We just need where things are changing, and that's what these, let's say this is a feature vector that's detecting horizontal lines in an image. So we first want to know where these horizontal lines are, right? And even that, if it's a slightly low resolution form of the image, that is okay. That will help us better understand or apply our models and help in computational efficiency.
And sir, my one question is that how we can manage the FPS, frame per second? Okay, we can compress our image.
That's, you're talking for a video, right? Video has,
yes.
Yeah, but we are now in on the images, right?
Okay.
Yeah, so we're not anywhere close to video. So forget about FPS there, because that has to be handled very differently, right? Images, they have a specific dimension, right? So depending upon the type of sensor that took the image, you might want to downsample. You might downsample the image even at the time of presentation, or as it goes through these feature extraction layers, you can reduce or downsample the image by changing the stride of the convolution. So instead of convolving at every pixel, you convolve at every other pixel or the third pixel or the fourth pixel and so on. So that helps you improve a lot of things about the performance.
Sir, is there any way to calculate the stride? Because if suppose if we take a bigger stride, then probably we are going to, so as you just mentioned that the horizontal, to detect the horizontal line or the vertical lines, so maybe we are going to lose that, because we are skipping too many
Yeah, of course. It depends on the resolution of the image. I'm going to show you one real image example in the next slide, actually. So we'll have a look at, there I did not play around with the stride, but you can see that at what levels do you actually lose information from the image when you're doing that, right? Then that will give us some idea about, okay, let's not use such a big level of stride so that we just completely lose all the information, but a reasonable level of slide. So if the image is like super high resolution, right, a reasonable level of stride like 2 or 3 would not have too much of an effect. In fact, it will help us improve the performance of the model. At the end of the day, you don't need all that redundant information to make the decision of whether this is an image of a cat or a dog. It might be done in a better way. Okay, so that's the idea.
So this stride is something that we define. It's a sort of a hyperparameter, right?
Yeah, exactly.
And depending on the stride, the kernel that it learns can be different.
Depending upon the stride, what the kernel tells you can be different. Yeah, possibly. I don't see how that would work out. I'm not able to imagine in my mind how that could be possible, but maybe there is a possibility that could happen too. Yes. In fact, for images that have very sharp contrasts, right? Like for example, I'll tell you about the astronomical images, right, where you take a dark background and some few stars on it, right? Now, if you take a very big stride there, you might miss certain points which are important, right? But if you take very small strides, you might pick certain noise, and you can pick that as a star instead of some, camera or sensor noise that was entering. So there is a trade-off there, right? So you got to be careful about it. Okay. All right. So the idea of feature maps from kernels, right? Like we now talked about convolution, you understand how 1D, 2D, and 3D it works. But let's simply talk about how you can extract feature maps from, say, real world images, right? Let's take, for example, this image of a temple, right? Now, if you can see that this temple has several features in it, right? Now, there are certain low-level features, there are certain very high-level features, which will talk about the shape of the temple and so on. But if I take that same kernel that we were discussing right now, yeah, and apply on this image, what are we bound to get? So I'm actually grayscaling the image, okay? I'm just showing you a representation of that here. But when I'm applying this kernel, I'm grayscaling the image. So I'm not doing a 3D convolution. So what will you expect?
All the horizontal edges will be
revealed. So something like this. So this is my output. Yeah. Right. So here in this image that you can see that more from the main picture, this can tell you all about the horizontal lines in the image. And in fact, there are, although perspective wise, these are not horizontal, but they have some level to which there is a relationship between, or the convolution or the dot product between this kernel and those points here seem to highlight these lines, which are not completely horizontal, but you can see that these horizontal lines are all highlighted. The same way, if I just rotate the kernel, what would I get?
Vertical edges.
The vertical edges, yeah. So something like that, right? Right. So these are basically highlighting all the vertical edges. You can clearly see here, right? These lines here are now telling you about the vertical edges. Now, these are what are called feature maps, right? Oops, sorry. These are your feature maps.
So one general question,
like
feature selections will happen after the convolutions between kernel and image.
So once you convolve your image with a kernel, you get a particular feature map, right? In this case, this feature map is representing those places in the image where there is a horizontal line. And which
So
you
in
can
this feature map, we can pick any feature, right, which we want.
as in this itself is a feature, right? In some sense, this is telling you about the image, and it's telling you specifically that these are the places where there are horizontal lines in the image. Okay, so in some sense, this itself gives you what are the features that are there that is corresponding to a horizontal line. And same thing for here. In fact, more these are pretty low level features. This can be passed through several more convolution layers to give you much more complicated features of the image, right? So this is just an example to illustrate the point.
Sir, can we also have I mean, just like we have horizontal, vertical, there can be a feature which can give the inclined features.
Yeah, of course, all that can be done. No, that's what I'm actually coming to that point in the next slide, which will make everything clear, right? But my only thing is, what I wanted to tell you from this is that when you convolve the kernel onto such an image, these are the specific types of features that you are able to extract, correct?
Okay.
Right, in this case, vertical and horizontal line. And in fact, as
It means that, like, in one convolution, you will got one feature like that.
one feature map, exactly.
So
Yes.
how many features you want to track, you have to do that.
Absolutely, you can decide that many number of convolution layers that you want to have, or the convolution kernels that you want to have in a single layer too, right?
Okay.
At the
So
end of
like,
the day,
as beginning of discussion, we told, like, it's involve the hierarchical.
exactly.
So where is
Exactly.
that hierarchy here?
Here we are talking about just a single layer, right? Now after this can go to another convolution layer, right, where you have different types of kernels at this level.
Okay.
And that might give you much more complex features, which are, say, a combination of two horizontal lines here. Maybe it detects these guys. Yeah. And after that can combine, right? So now you are getting more and more abstract features of the image as you go up this hierarchy. So here you're still at a single layer, right?
So this means, like, how many layer means how many times you do the convolution with same image.
Exactly. Yeah. Now you can decide how many kernels you want at a particular level, and that can be set as well. So those are all things that you can play around with. But at the end of the day, how many n that you want, that is how much deep that you want to go into.
So the goal of this action is abstract feature selection, right?
Exactly. You're trying to extract these features from the image that will help you solve some objective, which is what classifying the image or telling something about the semantic meaning of the image and so on. Okay. So that's what you want. You want like an abstract representation of this image. And that representation is got as you go from layer to layer and performing convolution to extract these feature maps.
Sir, just one intuition. Can
Yeah.
this be done in some useful way to real-time data or any other data set apart from picture?
Exactly. Yeah. No, there is nothing stopping you from applying this to even time series data, right? In fact, you can take this and apply it to even weather data and start saying that if this is how the weather is, but you need to have something labeled, right? You can't have unlabeled data. You'll have to have, like, if this was the pattern of the weather, then this was how the weather outcome was, whether it was sunny or raining. What is that, right? And then you can give that to a model again and again and train it to extract very abstract features of what the weather patterns were, right? And that way you can still do this.
Any known
Doesn't
model to
matter.
you
Yeah.
that uses this into some type?
Known models. So CNNs you can think about CNNs to be used for any form of data that has some spatial or temporal correlation in it. So there is nothing as such that, but there are many variations. Like, for example, as I talked to you earlier, right, that VGG16 is one such model. ResNet is another model that has been used for CNNs, which I believe is on, if I remember correctly, on certain types of images. Images are often really good for such functions because they are nice 2D spatially organized data structures, right? Images are like that. So on the top of my head, I'm not able to recollect a specific application, but I will let you know. Okay, but at least the theory says you can apply it to any form of data that has some spatial and temporal correlation to it. Does not have to be images. Images are a very straightforward example. Right? That's it. Okay, so what's the main point that I want to say about this is, let's take another image like this, right? This is a much more modern building like image. You do the same thing, and this way you are getting both the horizontal and vertical lines. Okay, but what is the aim of CNNs? What are we trying to do with CNNs? We are trying to extract these features out to do something with it, right? So in essence, this thing is not something that we fix or decide a priori. We do not decide this a priori or fix this. This was just an illustration that such a kernel would give this. In fact, this is the entire domain of computer vision, right? What is computer vision all about? Is it possible for me in some very sophisticated way design filters or design kernels that can extract specific features from this image? Okay. In this case, I've shown you a very simple example of how horizontal and vertical lines are being extracted. But when deep learning came, the idea became that I do not care what this kernel is. I let the network figure it out, or I let the algorithm take over. Okay. So the bottom line is, we do not have to hand engineer this kernel. The training gives rise to these kernels that can extract specific features that will give rise to a specific objective, right? And what is the objective? I want to classify whether it's a cat or a dog or a zebra or whatever it is, right? Now, if there is an error, right, in that prediction, that error gets backpropagated across all these layers, and it will tweak these kernels, right? It will tweak the shape of these kernels, so that next time when it's then the same image or similar image passes through it, there is a better chance that you will be able to predict that it is an image of a, in this case, a building. I'm just giving you an example. Yeah. So do you understand that? So this is something that we don't face. This is something that the network learns, right? So at the end of the day, when we actually train a CNN and it works well for a set of images, we can then investigate both these feature maps and these kernels, how they look like, and exactly understand what sort of features are they extracting from this image.
So one thing, like when back propagation will happen, so kernel will learn from that back propagation.
That error, exactly.
Error is
that delta, which is back propagated through many layers.
Yeah.
The kernel will take in that error and it will update the weights.
Okay, means he will update himself, right?
Yes.
To predict next time this.
Predict. Then that means the shape of the kernel slightly changes, right?
Yes, yes.
And that way, what happens is that tells you what sort of features are being extracted in order to make a better prediction that that is a building, rather than something else, right? Maybe a temple or something else, or a landscape. So for example, these are your three classes of images that you're giving. You're giving buildings, temples, and some landscapes. Right? So what are the features of these that make it building or more buildingy, to use that term? So those are the ways in which the kernels will learn. So you do not have to hand train them. In fact, that is why deep learning evolved, right? That means you do not figure it out. You let the network figure it out. And then you study the properties of the network. And in fact, then it will tell you what is actually the shape of the kernel, because the kernels can even be nonlinear, right? Because you are passing it through a nonlinear ReLU function at every stage, because after you do the convolution, you pass it through activation functions. And in fact, if you pass it through an activation function, you can imagine places where it's dark will become more darker, places which is bright will become more brighter, right? So it will highlight certain features of the image much more sharply. The contrast will come out much more effectively. And that way you'll be able to separate out certain features very easily from the image. And that might be helpful for distinguishing what the image is about.
So at final, when we will pass it all through the activation function, we'll submit up all the outputs from different kernels that we have, right?
So when we do it with the ReLU, you can keep it separate too. Then it will become, at that level, you can have a convolution of many such feature kernels, or you can add them up too. So there are many ways to do this. I believe if we go back to the architecture, where do we have it?
Is this only valid for supervised
So
language?
here, right? This is, I mean, this is still supervised, right? So here, can you see this, right? This is a pooling layer, right? At this level, you have 1, 2, 3 layers or 3 feature maps. At this level, you can have many feature maps, right? Not just 3, depending upon the number of kernels that you use. So this can have, say, if this is an M layered feature map, this can be N, where N is greater than M, right? Now here it increases further, okay? So O layered and so on. So it depends upon the number of kernels that you use at this level. That many levels, layers of results. And in fact, the kernels itself give you a way to sum everything up, right? In this case, right? Because if I use, this is an N layered result, for example, this we need to use an N layered kernel, correct? And that will give you one such frame. And you use many such kernels, that will give you many such frames. Okay? And each kernel can be some linear combination, convolved combination of any of these layers that you are using. Okay? The network will figure out how to add them up, basically, which combinations to add them up in order to give you the next result that can help you extract features of the image that will help it to be classified better.
Sir, what is pooling here? Can you just...
I'll talk about pooling next. But how much time are we in? 11:10. Okay, we have 5 more minutes. But I'm going to talk about pooling next. So you don't have to. Right. Okay, but people are okay with this. People got this idea, right? That is, we do not have to hand engineer them. This is actually figured by the network. So, and that's the whole point of using the CNN in the first place. Okay. And finally, the pooling operation, right? Reducing the dimensionality. So how does pooling work? We want to understand that. And let's take a very simple example. Let's put it into perspective first. And that way we'll know what pooling actually does. Right? So again, the idea of pooling is downsampling. So stride and pooling do very similar things. Stride does it before you even apply the nonlinear activation functions, because you're doing it at the level of the convolution. But pooling, you do it once you are having the image. You can do the pooling at that level after there is convolution involved, right? The output of the convolution. There are 2 types of pooling approaches. One is mean pooling and another is max pooling. And the method that you choose entirely depends upon what is the objective that you want to do, right? What is the thing that you actually want as your objective? That decides max and mean pooling. There is no specific strategy of what to do, but let me tell you what is mean pooling and max pooling and give you the intuition behind it. Then you will know which sort of problem a max pooling will help and a mean pooling will help. So let's talk about mean pooling. Let's take, this is your image, for example. Okay, this is the image. These are some pixel values of the image. Okay. After, say, this is the output that you got after your convolution. Let's say, for example, this is the case. Okay. Now, what is mean pooling is very similar to a convolution again. In fact, what you are doing is now you're convolving the input with a kernel that has equal contribution of all these pixels that you want to pool together. So that means you're taking the image and you're trying to shrink the image, right? And how you are shrinking it is you're looking at one part of the image and you're placing the kernel on top and taking the average pixel value in that particular location. So the output of pooling will look like this. So you take this, and then next time you put the kernel here. So you do not overlap. These are non-overlapping operation. It's a non-overlapping operation. So you do not overlap. You push this and then you come down. And so in essence, the output image is now smaller than the input size, correct? And the pixel value at a specific location is the average of all the pixels. So in this case, this is the output of pooling. But what is the consequence of this? I'll tell you. Yeah.
So one thing I want to know, like this, now this pooling is related to the compression of information, right?
Compression of information. Yes. So you are now saying that, okay, this is my feature. So let's take this example. This is my feature at this level, right? Now I want to pool some of the relevant stuff from this, right? So I can do that in two ways. That means I take this small part of the image and I average the pixels out here. And then I take this part and average the pixels out and so on. Right? So, and then you go here, and you do that. And then you get like a smaller version of the image, which with certain features from this pooled together or highlighted. So when I tell you about that, I'll explain that a little bit more, then it'll become more clearer. But that's the point. Okay. Now, then in that same sort of sense, what is max pooling? Anybody?
Can we increase?
What will be max pool? So if this is mean pooling, that is you just take the mean of these pixels and then you place it there.
So we will include the overlapping so that it can be increased.
No.
So we'll take the maximum of the values.
Exactly, that's it. It's very simple. There is no kernel at that point because there is no kernel that can implement a max function. Because if you can imagine, okay, why can't a kernel implement a max function? Any idea? Anybody?
Because overall that definitely going to be more smoother if you introduce kernel there.
No. I mean, why a kernel approach cannot be used to implement a max function?
Sir, because every
kernel is a summation of
will have a different max value.
No. Someone said summation. What was that?
Kernel is a summation operation. It's a dot operation, right? And we are looking for maximum value.
Very good. So maximum is a non-linear operation. It cannot be obtained by a function or an operation that's linear in nature, which is what the kernel does, right? So that means what we have to do is we have to go at every point and figure out what's the max value. So in this case, max is 70 and 70, 50 and 35, 90 and so on, right? So this is the output of pooling, and this is how max pooling works. So this is mean and this is max pooling.
So means that like mean and max is a logic finding the next number, right?
Sorry?
Here, mean and max word is a logic, right? Here we are taking a mean.
Here we are taking the mean, here we are taking the max. Yeah, it is exactly what the word tells you, right? Mean pooling is you pool and you take the mean of all those pixel values. Max is you just take the maximum value of those pixels and then you place it there.
So what if we have a kernel something like 1111? Even in that case,
just a summation, right? I mean, it's not the mean still.
So how we represent it when we define the stages of our network?
Right. I mean, you can have different types of pooling. There's even min pooling, right? Instead of taking the max, you take the min, Okay, but what I'm trying to establish here is what is the intuition behind doing this pooling, right? What does mean pooling give you? What does max pooling give you? That's much more important than what the operation is, right? Now, can anyone tell me what will be the consequence of doing a mean pooling? What does that help you? Why does that help you? Instead of, yeah, why does it help you? Any idea?
So, sir, to deep dive into the exact feature of the particular image.
Think about it a little bit.
Smooth values find
map.
Edges.
Yeah,
max pooling related to edges. Mean pooling smooth values.
That's almost there, but will be a little elaborate that a little bit more. So imagine this is a feature map that you got at some level, okay? And imagine that this is a very noisy image, okay? The noisy feature map, okay? Now, if it's a very noisy feature map, or in fact, even if the image was itself very noisy to begin with, which method do you think will work better in terms of extracting good features? Will the mean work better or the max?
So mean
works better.
Mean would work better because mean is like the smoothen the image. So mean will be like a low pass filter. Mean pooling. Okay. So it will wait. Sorry, I just changed it. This is this. Okay, sorry. This is for this. Smoothens the image, right? Mean smoothens the image. So it's more like a low pass filter. It's useful for very noisy data. So if the data itself is very noisy, then mean pooling will help you average the noise out and protect the signal in some sense, right? Because if by averaging you get rid of the high pass or the high frequency information. So it's like a low pass filter. Now the max, I've just put the answer up, highlights more sharp features. Okay. Now I gave you this example, right? Like if you have an image of the night sky, right, with stars, right? Now this is a very sparse data. Okay. Now if you have computed certain features, right, maybe a cluster of stars, something like that, right? If you want to identify whether it's a single star or a cluster of stars, you want to improve contrast in this, right? That background is dark, the things is bright. So what you would like to pick up from a given location is, instead of the average value, which will actually blur this out, right, and smudge this out, you want to pick the max value, which will enhance contrast. Correct? So imagine in this case, come back. In this case, to identify these edges, okay, very effectively, would I use mean pooling or max pooling? Or which would be better?
Max pooling.
Very good. Max pooling, right? Because in this local area, it will pick up those lines much better, right? And at the end of the day, if you push this through max pooling, you might be able to detect these lines very well compared to this, right? So in fact, what you can even do is, if the input is very noisy, initial layers can have mean pooling, and then the later layers can also have max pooling. So you can combine some ideas like that too, right? And this is where research goes into play, right? Like you play around with this and actually find out what works best, but you always keep in mind the problem that you're trying to solve and what sort of data you have at hand and what methods will be able to best reach the objective that you are trying to do with that data. Okay.
So in case of the point where we talked about the noise, right? Mm-hmm. So mean will actually sort of include the noise also, right? I mean, if we take
no, it won't, right? Like think about this. Let me give you a simple example. Say this is your signal, okay? let's say this is the signal of interest. Okay, let's say this is it, but it has, but your data looks like this. Okay. Now, if I just take a simple moving average, right? That is, I take a small window and then I take the average, right? All the local noise will become suppressed because noise varies up and down, it will cancel out, right? And then I'll get the signal. So in essence, I get the signal out from the noise. So anything that's very high frequency will be filtered out. So this is what mean or moving average, this will give you. Okay. So say apply the same thing to the image. Okay. If an image has some signal in it, that is some pixel values, but it's highly noisy, that means locally things are varying too much. If you take the mean of all these points, you preserve the signal, but you get rid of these unnecessary variations.
The thought process that it makes sense, sir, as you mentioned. But the thought process was that the noise will be, will be there, but slightly less, and it
will be lowered, but it will be lowered. It will be there. I won't say it goes away, but it will be lowered, right? Because that's what you're trying to do. Anything that's uncorrelated noise will get abolished. So I have to be a bit more specific. When you take a moving average, uncorrelated noise, right? Like salt and pepper noise and all that, that will be suppressed, because if there is correlated noise in the image, because what I mean by correlated noise is that the noise value of one pixel depends upon the noise value of the other pixel in some way. That might be harder to remove compared to if there is some random noise applied to each pixel independently.
Okay. What I was thinking was that if we take the max will actually give us the original. I mean, mostly.
But imagine, right? If one of the pixels here was the max, but that was something that was more noisy, then you are picking more noise from the image rather than the signal. So you have to be careful about that. Okay.
Yeah.
All right. So I think let's stop here, guys. I think it's already 11:25, but hopefully this gave you an idea of what sort of operations are happening at the network level, right? Like you can imagine now what the network is actually doing. It's extracting features, pooling such features together. That acts as the next input to the next layer, and there more complex features are getting extracted, there things are getting pooled, and so on and so forth, till you reach a stage where you are able to compactly represent the input image and still maintain the spatial relationship, right? Where is that? Yeah. Still maintain the spatial relationships in the input. And finally, we take it to, and we flatten this out and we use it for many purposes, right? That we want to classify things and so on and so forth. Okay, but we'll discuss about the fully connected and the softmax part next week. That's the only thing that's remaining, but I hope the other stuff was clear. Yeah? If there are any questions, if people have other things to do, please, you can leave, but if there are questions, I'm happy to answer. Okay. Cool. I'll stop recording.